Let's solve problem 7.19 for Microelectronic Circuits 8th edition by Sedra and Smith. Consider the amplifier of this circuit when operated with a supplied voltage VCC equals 3 volts. Part A asks, what is the theoretical maximum voltage gain that this amplifier can provide? So in general, we can calculate AV, the gain, as VCC minus VCE divided by thermal voltage. In order to get the theoretical maximum gain, we need to understand that VCE near saturation is equal to 0.3 volts. Anything less than 0.3 volts means we're outside of saturation, and we want to stay in saturation. So therefore, this 0.3 volts is the smallest value of VCE we can use while staying in saturation. So therefore, the maximum will be VCC, 3 volts, minus smallest possible value of VCE, which is 0.3 volts, divided by the thermal voltage, which is 0.025 volts. So I calculate 108 volt per volt. Okay, let's move on to part B. What value of VCE must this amplifier be biased at to provide a voltage gain of negative 60? So we have negative 60 volt per volt is equal to negative 3 minus VCE divided by 0.025. And now we just need to solve for VCE. I need my calculator. So let's multiply 0.025 to 60. And of course, these negative signs are just going to cancel out. So we have 60 times 0.025. So I have 1.5 is equal to 3 minus VCE. So therefore, VCE will be equal to 1.5 volts. Okay, now let's do part C. If the DC collector current IC at the bias point in B, so meaning we're biasing VCE to 1.5 volts, and we need the DC collector current IC to be 0.5 milliamps, then what value of RC should be used? Okay, so VCE here is 1.5 volts, IC is 0.5 milliamps, so we can solve for RC as VCC minus VCE divided by IC, which is 3 minus 1.5 divided by 0.5 milliamps, and that is equal to 3 kilo ohms. All right, let's keep going with the next few parts. All right, let's keep going with part D. What is the value of VBE required to provide the bias point mentioned above, which was IC equaling to 0.5 milliamps? Assume that the BJT has I sub s equal to 10 to the negative 15 amps. So we can leverage the following equation, that the collector current IC should be equal to I sub s times e to the power of VBE divided by VT. And we just need to solve for VBE. So let's divide IS to the left side. So we get IC divided by IS is equal to e to the power of VBE divided by VT. We can take the natural log of both sides. So we'll have the natural log of IC divided by IS. Now the exponential will drop to the base. It's equal to VBE divided by VT. And the natural log of E is just 1. So now we just need to multiply VT to the other side. So we get VBE is equal to VT times the natural log of IC divided by IS. And now we just need to plug in our values. So that'll be 0.025 volts times the natural log of 0.5 milliamps, which is 0.5 times 10 to the negative 3 amps, divided by IS, which is stated to be 10 to the negative 15 amps. And I get that VBE is equal to 0.673 volts. Okay, let's move on to part E. If a sine wave signal VBE with a 5 millivolt peak amplitude is superimposed on VBE, find the corresponding output voltage signal VCE that will be superimposed on VCE assuming linear operation around the bias point. So basically we have a sine wave signal with a peak swing of 5 millivolts. And in order to find the peak swing on the output, VCE, we can do VCE is equal to the gain times the VBE swing. So let's solve for that. So maximum output swing will be negative 60 volt per volt times 5. Now you want to be careful with this. It's going to be 5 times the sine wave. So we're going to do sine of omega t to get negative 300. This should be millivolts. So it's going to be negative 300 sine omega t millivolts, which is also just equal to negative 0.3 sine omega t volts. So what is this sine omega t? So we have a sine wave signal for VBE. So it's looking something like this, and omega would be the frequency of that sine wave. So you need to make that distinction. It's not just a DC signal. This is an AC input signal. Okay, now I'll solve for parts. F, characterize the signal current IC that will be superimposed. So now we have, not only do we have a AC sinusoidal voltage signal, but it's also going to produce a AC sinusoidal current signal. And that's going to be equal to its IC, right? So we're interested in this wire. So that's going to be, this will be the AC max output divided by RC. So we're going to get basically 0.3 sine omega t divided by RC. What was RC? It was I'm drawing a blank. What was RC? We calculated it in the last problem. Three kilo ohms. Sorry about that. 3 kilo ohms. We calculated that in part C. Okay, so that's going to be 0.1 sine omega t milliamps. Let me write that up here. So our current will be 0.1 sine of omega t milliamps. All right, let's move on to the next few parts. All right, part G. What is the value of the DC base current IB at the bias point? We're going to assume that beta equals 100, and we're going to characterize the signal current IB as well, lowercase ib, that will be superimposed. Okay, so first off, IB is equal to IC divided by beta. So IC is 0.5 milliamps, beta is 100. That's going to be equal to 0.005 milliamps. And we can do the same thing for this lowercase IB. We're just going to do IC instead. So lowercase IC was 0.1 sine omega t milliamps divided by 100. So that means we get 0.001 sine omega t milliamps. Okay, let's do part H. Dividing the amplitude of VBE by the amplitude of IV, evaluate the incremental or small signal input resistance of the amplifier. So So basically saying input resistance is equal to the amplitude of VBE divided by the amplitude of IB. So that's going to be the amplitude, which is basically the term leading the sine function. So the leading term for VBE would be 5 millivolts. In the last problem, here you can see the leading term for IB is 0.001 milliamps, and that's equal to 5 kilo ohms. Okay, there's one part left to solve. Let's wrap up with 7.19. So part I says to sketch and clearly label graphs for VBE, VCE, IC, and IB versus time. Okay, so we can start with VBE. So we have time here. Now notice it's a lowercase v and an uppercase B and E. So that means we're trying to graph the DC and AC components together. So first I'm going to label my DC, capital VBE, which was 0.673 volts. So this is not the graph actually, I'm just kind of labeling this here. 0.673 volt. Okay. Now, our small signal VBE had an amplitude of 5 millivolts. So what that means is we're going to have a sinusoidal change of 5 millivolts basically. So this would be our actual VBE curve. And each peak is 5 millivolts. And this is going to be pretty similar for the rest of these. So we can do VCE and key. So our capital VCE, our DC component, is 1.5 volts. And our small signal amplitude was 0.3 volts. Remember, this was the max we could do without saturating the transistor. So we'll have something like this. So the amplitude is 0.3, which means our peak value is 1.5 plus 0.3, so 1.8 volts, and then our minimum value is 1.2 volts. We have our collector current graph, so our DC value was 0.5 milliamps. And our small signal amplitude was 0.1 milliamps, if I remember correctly. So we're going to go up and down with the amplitude of 0.1, which means our max value is 0.6 milliamps and our minimum value is 0.4 milliamps. So not enough room for IB, but it's the same process for all of these. Hopefully this is becoming clear. We have an AC and a DC component to the graph. Thank you for watching my video. For any comments, questions, or video suggestions, feel free to reach me in the comments section or by email. Thank you. Have a great day.